Hello everyone. In this video, I'll be explaining about the medicinal and industrial applications of coordination and organometallic compounds. So first coming on to the sodium salt of calcium chelate of EDTA, which is used in chelate therapy. So here you can see this is the structure of EDTA, which has an affinity towards metal, which is in the M+2 state. So this is the structure of metal EDTA complex. Now, suppose there is a condition of heavy metal poisoning due to mercury, lead, chromium, etc. So what happens here is EDTA is used to form a stable complex with these heavy metals. So once this metal EDTA complex is formed, it can be removed from the body by excretion. So for this sake, EDTA is used as an antidote for lead and mercury poisoning. So here you can see the two complexes, that is complex of EDTA with Hg+2 ion and with Pb+2 ion. So these two stable complexes, once they are formed by EDTA with these heavy metal ions can be easily removed from the body by excretion. So now for this sake, this complex, that is the sodium salt of calcium chelate of EDTA, is administered into the body so as to bring about the removal of heavy metals from the body. So next coming on to the use of cisplatin in cancer therapy. So what is cisplatin? So this is a structure of cisplatin, which is a complex of platinum with two chloroligands and two amine ligands. So here this cisplatin is widely used in cancer therapy, which is believed to bind to DNA and interfere with its replication. And once this replication is stopped, then what happens here is ultimately it will lead to cell death. Okay, so first step what happens here is one of the chloroligands will be replaced by water. So what happens here is the cisplatin is administered into the body. Once it passes through the cell membrane, this chloroligand will be replaced by water. Next, one more chloroligand will be replaced by one more water molecule. So you can see here, yeah. So this is the cisplatin. Once it passes through the cell membrane, one water molecule will replace one chloroligand. Okay, so you have two amine ligands as well as one chloroligand and one chloroligand which is replaced by water molecule. Again, one more water molecule will replace this chloroligand also. So we have platinum complex with two amine ligands and two water ligands or the aqua ligands. So now, once this happens, you can see that this structure, that is the cisplatin complex without the chloroligands, which is replaced by water ligands, will be coordinating with the DNA. So coordination is also very specific. It will coordinate with the guanine residues of the DNA. So there are three different possibilities. One possibility is it will coordinate with the two guanine residues of the same strand. Okay, so this is one strand, the same strand. So two guanine adjacent residues. So these two residues will be coordinated with the platinum by the removal of these two aqua ligands. Okay, so this will specifically coordinate with the nitrogen of the guanine ligand, residues. Okay, so here one possibility is two guanine residues which are adjacent to each other and which are belonging to the same strand. One more possibility is it can coordinate with the guanine and adenine of the same strand, and these two may not be adjacent to each other. Okay, so the third possibility is it will coordinate with the two guanine ligands of different strands. So this is of one strand, this is another strand of DNA, and these are the two guanine ligands. So usually much preference is towards this condition, that is when it is coordinated with the two guanine which are adjacent to each other and two guanines belonging to the same strand. That is accounting to around 65% cases. Next, 25% of the cases where it will coordinate with guanine and adenine, whereas remaining very small percent of the cases it will coordinate with two guanine ligands of the different strands. Okay, so coordination will take place like this by the removal of aqua ligands and coordination with the nitrogen atoms of this guanine or adenine residues. Yeah. So this is again a picture showing the different possibilities. So two guanines which are adjacent to each other, adenine and guanine. Okay. So these are the guanines of different strands. Here guanine with some other nucleotides in between them. Okay. So here we have, okay, yeah. So once this complex is formed between the cisplatin as well as the DNA, it will attract the repair proteins. Okay. So once these repair proteins come, they can't identify this altered structure of the DNA because it is not the actual DNA which is present now. It is coordinated with something extra here. This extra is nothing but the cisplatin molecules. So because of this changed structure of the DNA, the repair proteins can't act very effectively. So if there is no repair, then what happens here is the replication cannot take place. If the replication cannot take place, then what happens ultimately? See, here you can see this results in interference of DNA replication because repair mechanism cannot work effectively because of the altered structure of DNA, and hence the cell multiplication is also stopped. So finally it will lead to apoptosis or the cell death. So that is how the cisplatin actually works. Now you can think of the question, why the transplatin? So you can just imagine the cisplatin structure, you know the structure. Let me come back to it. So this is a cisplatin. So here we have two amine ligands at one side and two chloro ligands on one more side. So if we speak about the other geometric isomer, that is a trans isomer, that is transplatin. So NH3 will be here, NH3, Cl and Cl will be on the opposite side in case of transplatin. Why it cannot act as an anti-cancer agent? So I think you've already got the answer. So suppose if the two chloro ligands are opposite to each other, then once they are replaced, the two aqua ligands also will be opposite. They won't be on the same side. Then do you think such type of coordination will be possible if two aqua ligands are on the opposite side? It's not possible, right? So because of this, the transplatin cannot act as an anti-cancer agent, whereas only cisplatin is effective as an anti-cancer agent. This is the answer. Yeah. So that was about the first two complexes which are used for different purposes. So next, coming on to the catalytic hydrogenation of alkenes by Wilkinson's catalyst. So this catalyst, which is a coordination compound, is called as Wilkinson's catalyst. So the name of this catalyst is chloro. So it has a chloro ligand, tris triphenyl phosphine. So this PPH3 group is named as triphenyl. This PH is phenyl group. There are three phenyl groups, so triphenyl phosphine. So there are three such ligands, and the prefix to be added is tris here. So chloro, tris, triphenyl phosphine, and rhodium. What is the charge on rhodium or the oxidation state? Here chloro is -1, so rhodium will have the charge of +1 because the overall charge on this complex is 0, or it is a neutral ligand, right? So we name the complex as chloro, tris, triphenyl phosphine, rhodium 1, or in common we call it as Wilkinson's catalyst. So it is used in the hydrogenation of alkenes. So hydrogenation is nothing but, let us take an example. Here we take propene, we add hydrogen. So these two hydrogens, this is nothing but two hydrogen atoms are there. One hydrogen atom will add to this carbon, one more hydrogen to this carbon. So we have the product as CH3, CH2, CH3. Okay, so we get propane as the product. So this catalyst is mainly used to catalyze this reaction of hydrogenation of alkenes to alkanes. Okay, yeah. So this is the catalytical cycle, how this Wilkinson's catalyst will catalyze the reaction of hydrogenation of alkenes to get the final product as the alkane. So it takes place in different steps. So let us go to each step one by one. Yeah. So first you can see here, this is the Wilkinson's catalyst which we take with rhodium with the 3 triphenyl phosphine ligands and one chloro ligand. So first step, what happens is one of the triphenyl phosphine ligand will be dissociated. So you get this tri-coordinated complex. First it will be tetra-coordinated. If one ligand is removed off, this will result in tri-coordinated complex. Now what happens is, in the next step, okay, oxidative addition of H2. Now I have to tell you something regarding this oxidative addition. Oxidative addition is nothing but addition of a particular compound or a substance to the complex so that the coordination number as well as the oxidation number of the central metal will be increased. Okay, so during oxidative addition, the coordination number as well as the oxidation number of the central metal will be increased. So here you can see this was a tri-coordinated complex. Now on addition of H2, this is added in such a way that the two hydrogens, H2 is nothing but H and H, right? The two hydrogens will be added separately to this rhodium metal. Okay, so you have PPH3, which is already here, one chloro ligand, and the two hydrogens which are split and added to this rhodium. So now the coordination number of rhodium has increased from 3 to 1, 2, 3, 4, 5. So the coordination number has increased by 2 units by the addition of this H2. Okay, so once this is formed, now the next step is you're adding the reactant. The reactant is nothing but the alkene. This alkene has to be hydrogenated to form alkane. So now we have taken RCH2, that is with a double bond. So it should be converted to the respective alkane RCH2CH3 as the product. So you add alkene, that is the next step, complexation with alkene. So alkene is added to this complex. So what happens here, this is a 5 coordinated complex. So this will get converted into a hexa coordinated complex. So this alkene will directly bond to this rhodium like this. Okay. So now what happens is, one of the hydrogen from here, okay, this hydrogen, there are two hydrogens, right? One of the hydrogens will add to this double bond. Okay. So once it is added, what will happen here is, this side of the metal will, this side of the carbon, this carbon is already coordinated with that of rhodium. You can see here, okay, and this carbon, to this carbon, this hydrogen is added. So this becomes, this terminal carbon is coordinated with rhodium. Here one hydrogen is added, so it becomes CH2, and this is nothing but R. Okay, so after complexation with alkene, the next step is intramolecular hydride transfer. So one of the hydrogen, which is nothing but the hydride in this case, intramolecular means what? Within the same molecule. So within the same molecule, one hydride is transferred to this double bond. Okay, so that this double bond gets converted into a single bond. Okay, so here rhodium is coordinated with this double bond as an alkene ligand, and now because of the hydride transfer, this terminal carbon is bonded to the rhodium metal. So we have RH, CH2, CH2, R. But now this is not the product. We want R, CH2, CH3. But here we have CH2. So now what we have to do? One more hydrogen, that is nothing but the hydride, has to get transferred to this carbon, so that we'll get R, CH2, CH3. I think it is clear. This is R. Here it is CH2. How we got this CH2? Because of the transfer of hydride from here. And here it is already only CH2, which is coordinated with this RH. Now to get the product, this CH2 has to be converted to CH3. So to get one more hydrogen, it is taken from this hydrogen, that is this hydride is transferred to this carbon, so that we get RCH2CH3. Okay, yeah. So here once even this hydrogen is added, then this chain is eliminated. Okay, because this is a product what we require. So it is getting eliminated as RCH2CH3. So this hydrogen is also removed as hydride. So what is remaining now? RH with chloro ligand and two triphenyl phosphine ligands. So you can see here finally we got this as the product. So we started with this, you added hydrogen, in the next step we add the alkene, then what happens here is intramolecular hydride transfer takes place, one hydride gets transferred here, in this step one more hydride gets transferred, and finally the product is removed off. So finally we get this catalyst from which we have started. Now on addition of one more triphenyl phosphine group, you get back the normal, the first Wilkinson's catalyst which you have taken in the beginning. Okay, so this is the catalytic cycle. We start with the catalyst, and once the cycle is completed, we get back the original catalyst. Okay, yeah. So that was regarding the Wilkinson's catalyst and the catalytic cycle. So coming on to the next application, the last application, that is Monsanto acetic acid process. So this process is the major commercial production method for the preparation of acetic acid. So we take methanol as a reactant and we get acetic acid as a product, and for this method we use this catalyst. Okay, so you can see this catalyst which is the cis isomer here. Okay, specifically cis isomer. So dicarbonyl, diiodo, rhodium, 1 anion. Okay, so we have this as a catalyst which will catalyze the conversion of methanol to acetic acid, and this conversion in the presence of this catalyst is referred to as Monsanto acetic acid process. And using this method, large amount of acetic acid is being produced. Okay, so it is a commercial production method for the preparation of acetic acid. Okay, so we'll start with the catalytic cycle again. So here you can see, in the previous slide I've shown it. See, this is the catalyst which we use, rhodium, which is coordinated with 2 carbonyl ligands and 2 iodo ligands, and of course it is an anion, right? So here we have this catalyst, okay, rhodium, which is coordinated with the 2 carbonyl ligands and 2 iodo ligands, and the charge of this complex is -1. Okay, so before that I want to tell one more thing. Methanol is prepared from syngas. Okay, so once we get this methanol, using this methanol we prepare acetic acid by making use of this catalyst. Okay, yeah. So once the methanol that is formed from this syngas, okay, we get methanol, CH3OH. It is made to react with hydrogen iodide, okay, Hi. So once these two are made to react with each other, we have the products CH3I. Okay, this CH3, it's very simple, CH3I, and you'll get one more byproduct as water. Okay, so we get methyl iodide with the reaction of CH3OH and Hi. Okay, so this methanol is obtained from syngas, as I've already told, and it is made to react with Hi to give these two products. Okay, so here we have taken the catalyst. Okay, so first step, okay, methanol obtained from syngas reacts with Hi to form CH3I. So next step, what happens? Just by seeing this you can tell me. See, CH3, there is I, okay, the CH3 and I is added to this. So in the previous method also we have seen, whenever a molecule is added and it is split and added to the central metal, then the coordination number as well as the oxidation state of the metal increases. So this is called as oxidative addition. So the same thing is carried out here. CH3I, methyl iodide, is added by oxidative addition to this catalyst. Okay, so that the coordination number increases from 4 to 6. Okay, so this CH3 and I are separately coordinated with this rhodium. Okay, yeah, so oxidative addition of CH3I. So the coordination number of this complex of this rhodium increases from 4 to 6 here. Okay, so next step is migration of the methyl group to an adjacent carbonyl group. So here you can see these two groups. Okay, acetic acid, we know the formula, it is CH3COOH, right? So what happens here is, here there is a CO group. So this CH3 group, which is adjacent to carbonyl group, it will migrate to this position. So it will bond with this carbon. Okay, so that what will happen here is C double bond O and CH3. Okay, migration of the methyl group to the adjacent carbonyl group so that you get C double bond O CH3. Okay, I think it is clear. Yeah. So here from 6 coordinated complex you get a 5 coordinated complex because cis CH3 has moved to carbonyl group to form this group. Okay. Now this 5 coordinated complex will react with carbon monoxide with CO to again get a 6 coordinated complex. Here there was 6 coordinated complex. By the migration of CH3 we got a 5 coordinated complex. Again on addition of carbon monoxide we get a 6 coordinated complex. Okay. So next step is very crucial. Here there is COCH3. These both will combine together to give CH3 COI. Okay. So this both will combine together to get eliminated as CH3COI. Okay. So reductive elimination to release CH3COI. Okay. So reductive elimination is nothing but here the coordination number of this metal will decrease. It is somewhat opposite to that of oxidative addition. In oxidative addition what happens? The coordination number increases. Here the coordination number decreases. And in reductive elimination the bond is formed between the two ligands. Okay, any two adjacent ligands. So here a bond is formed between these two, between this carbon and iodine, so that it will be eliminated as CH3COI. But in oxidative addition what happens? The bond is broken here so that the two groups are added separately. Whereas here the bond is formed between the two different ligands to form a separate molecule like this, so as to eliminate this molecule. Okay, so this molecule, that is CH3COI, is eliminated out. Okay, so once this molecule is eliminated out, it will undergo hydrolysis to give CH3COOH. Okay, so hydrolysis is nothing but addition of water. So water is nothing but H and OH. We can represent it that way. So OH will be added here and one H is remaining here. That H and I will combine together to give HI. So this HI can be again used to combine with methanol to give CH3I, that is methyl iodide, which is again used in this catalytic cycle. Okay, so here once the CH3COI is eliminated out, so these two are eliminated out. So what is remaining now? Rhodium with the 2 carbonyl groups and 2 iodo groups. So this is the one. So this is the original catalyst which we had taken in the beginning. I think it is now clear. So first we start with methanol and make it to react with HI to get this methyl iodide. Now here oxidative addition takes place. Okay, oxidative addition takes place, and then finally what happens here is, here is migration of methyl group to carbonyl group so that you get this complex. Next what happens? You have to add one more carbon monoxide so that here the 5 coordinated complex is converted into 6 coordinated complex. Then what you do is, here there is reductive elimination by formation of covalent bond between this carbon and this iodine so that this molecule is removed off. Okay, this on hydrolysis will be converted to acetic acid and HI, which will again combine with methanol to give this, so that the cycle will continue. So in this video I have explained the applications of organometallic compounds and coordination compounds in industrial processes as well as in case of medicinal applications of both of this. Okay, so hope the cycles as well as how the ligation takes place between that of metals and ligands, it's clear in this video. Thank you all for watching the video.